The GVSU Formula Racing Team has sponsored the project of an engine dynamometer. This project was designed by a team of 6 senior engineering students: John Santos, Noah Bolo, Alex Brook, Zachary DeVos, David Dragowski, and Austin Beardsley. The advisor for this project is Dr. Bain. The Engine Dynamometer project was sponsored by GVSU's FSAE team. The FSAE team builds a formula car each year and races it in a national competition. Historically, GVSU's FSAE team has struggled to quantitatively assess engine performance, and the team was only able to test the engine during a limited time window as they previously only had access to a partially functional chassis dyno. The team recognized the substantial benefit of being able to test the engine while it was not in the car, as the engine spends most of the build phase on an engine stand. This dynamometer will allow the team to test the engine during a longer period of time during the build phase and assess and optimize more engine parameters than they were able to previously. While defining the scope of this project, physical and mechanical specifications were defined. The dynamometer will be able to accurately and precisely measure horsepower values between 10 and 100 horsepower. Given that horsepower is a function of torque and RPM, the dynamometer will be able to measure torque values between 10 and 140 foot-pounds and record RPM values up to 4,700 RPM. Once data has been acquired, the dynamometer will then be able to graphically display horsepower and torque as a function of RPM. To increase the functionality of the dynamometer, it will also be able to link to the engine's can. The dynamometer will also be able to accommodate a variety of powersport engines while fitting within an agreed-upon footprint. Also, when in operation, this dynamometer will also be able to be operated by a single person and will be equipped with a comprehensive user guide to assist the operator. An engine dynamometer, commonly referred to as an engine dyno, is a machine which measures force, torque, or power output of an engine. The dyno is designed to apply a load to the engine at various engine speeds and measure the resulting force output. 3 commonly used engine dynos include the water brake dyno, which uses the resistive force of water being pushed through a turbine to create the resistive load. This design is beneficial because of its lower cost and simplified electrical design. The second, the electric motor dyno, which utilizes an electric motor to apply force against the engine's directional rotation. This dyno type is desirable because of the motor's ability to hold a steady force over a wide RPM range, and its ability to instantaneously change the resistive force. And the last, the eddy brake design, which we opted for. This is the design shown in the diagram. As you can see, the engine is coupled to an induction disc. When the engine is running, the disc will spin at the same RPM as the engine. The coils shown on either side of the disc are used to apply a magnetic field into the rotating disc. This field will cause the disc to resist rotation. A strain gauge attached to the coil casing will allow for an accurate reading of the force being produced by the engine. The entire assembly will be held in a closed-loop control by the dynamometer controller, which will vary the current through the coils to apply the desired amount of resistance to the rotation. This design shares many of the benefits with the electric motor design, but is far more affordable. Once completed, the GVSU Formula Racing team will use their engine dyno to adjust engine settings such as spark timing, fuel-to-air ratio, or mechanical airflow design iterations and determine the effect on performance, allowing the team to effectively tune their engine to peak performance before ever installing it into the vehicle. Initially, the engine will be installed as shown. Then a protective cage will be attached for user safety. Once everything is connected, the user will operate the dynamometer from the back of the cart. Here, they will have access to mechanical engine controls and a USB plug-in to connect their laptop to the onboard electronics. We chose the Telma AF5055 as our eddy brake for its low cost and ability to provide ample braking force for our application. The AF5055 is capable of producing 443 foot-pounds of braking torque at up to 5,000 RPM. Our design limits the application to 4,500 RPMs and will be used on engines up to 100 horsepower. This results in a maximum torque application of approximately 125 foot-pounds. Telma recommends that an eddy brake used in a dynamometer application be rated for at least 3 times the maximum torque output of the engine being tested in order to prevent damage to the eddy brake unit. the 125 foot-pound peak torque of the system falls comfortably within the recommended range of up to 147 foot-pounds. The powersports PWS3 power supply was chosen to power the eddy brake for its ease of control and ability to directly couple with the system controller. The power supply receives a 0 to 5 volt PWM signal from the controller to regulate the current flow to the eddy brake. Regulating the current supplied to the brake unit will vary the braking force generated. We selected the Your Dyno instrumentation kit as our system controller for its functionality, wide assortment of add-ons, and its low price point. This is an open source dynamometer controller with a comprehensive support community. It offers the standard inputs of 2 RPM readings, CAN data, a thermocouple, and 2 load cells. Additionally, it has 3 auxiliary inputs for additional data the user may wish to record. The controller will create a closed loop using the RPM sensor, the load cells, and the eddy brake control output in order to properly regulate the braking force applied. The state diagram shows the operation states of the FSAE engine dynamometer. At the top, the startup sequence of switching the key switch to the on position and disengaging the e-stop is shown. Then the testing setup is performed. Following the test setup steps, the testing in progress loop is shown. This section shows the different steps that will be taken in testing. Most importantly, during the testing, the dynamometer will check for hazardous conditions that would cause damage to the engine or the eddy current brake. In the event that the hazardous conditions are encountered, the testing will stop and power will be cut. Following the testing, the horsepower and torque curves will be output as a function of the RPM. The instrumentation kit from Your Dyno works with its own software for configuration and data acquisition. Configurable gauges and displays show current values of display and sensors for easy monitoring. Following a test run, the software outputs a graph of the torque versus RPM curves for insight into the performance of the engine. The Your Dyno software also allows for customized plugins that were used to protect the system by cutting off power at 4,750 RPM. Throughout the entirety of the design process, our main objective was to design a dynamometer that met all of the constraints and specifications while ensuring the dynamometer operator would stay safe. This slide displays an isometric view of the complete dynamometer assembly. The following slides will highlight some of the main mechanical design challenges and how these challenges were overcome. One specification that we anticipated would be a challenge was ensuring that the dynamometer could mount a variety of engines. We overcame this challenge by designing a highly adjustable engine mounting assembly that would attach to each mounting location on the engine. An example of one of these mounting assemblies is shown on the right. T-channel plates will be used for side-to-side adjustability. Large threaded rod will be used for vertical adjustment, and tensioning bolts will be used to move the engine closer to or further away from the eddy brake to properly set chain tension. Also, a chain-driven system was used to couple the eddy brake to the engine so that regardless of engine output, eddy brake input could be optimized using sprocket selection. Eddy brakes are not specifically designed for dynamometers. As a result, one challenge we faced was creatively designing an eddy brake mounting system that could be used as a dynamometer. Through the use of shaft design and shaft analysis procedures practiced in mechanical engineering courses, a custom yet cost-effective eddy brake mounting system was designed. This mounting system would allow the center portion of the eddy brake to rotate properly so that as a load is applied to the brake, the braking force can be used to measure the performance of the engine. The eddy brake was sprocket driven so that the engine output could properly be geared down for the eddy brake input. As previously discussed, sub-assemblies were carefully and strategically designed. In order to secure the sub-assemblies, a custom cart frame was designed. The challenge of designing this cart frame was to ensure user safety while properly supporting all sub-assemblies. To keep the user safe, the entirety of the dynamometer will be enclosed with sheet steel and wire mesh compliant with the FSAE safety standards. The mesh will be used to protect the user from unforeseen failure, and the sheet steel will be used to block any fluids from reaching the user while also directing airflow past the eddy brake. The figure on the right shows the components of the custom cart frame. The lower component will be made of 3-inch square tubing and support the eddy and engine. The removable portions shown above the base will be attached to the base using custom resin mounts to dampen potential vibrations from reaching the user area. The removable portion of the cage, shown up and to the left, will be simply pulled off to facilitate engine placement, engine adjustment, and engine removal. Due to the coronavirus outbreak, we were unfortunately unable to physically build the designed dynamometer. In lieu of building the dynamometer, several additional deliverables for the project were created. First, the entire cart was analyzed for deformation to ensure that the engine or eddy brake would not cause undesirable effects on the cart. Secondly, a thorough heat transfer analysis was performed to study how the engine and eddy brake would heat both certain areas of the cart as well as the engine bay as a whole. A plot of the engine bay room temperature versus time is shown. Next, since the dynamometer could not be built, a step-by-step document was created so that the Formula team could build the dynamometer. Finally, a user guide was created that explains how to start up the dynamometer as well as how to calibrate it, perform routine maintenance, and the limitations of the dynamometer so that no user error causes damage to the dynamometer. While we are unable to build the assembly, the simulations performed show that the design will meet or exceed all critical criteria. Thank you for watching, and we look forward to your questions during the live session of Design Day.